This video looks at the inverse of 2 by 2 matrices. So the inverse of a 2 by 2 matrix A is the matrix we pre or post multiply by A, and the product is the identity matrix. The inverse is denoted by A to the power of -1. So A to the -1 pre-multiplied by A is going to equal the identity matrix I, and A to the -1 post multiplied by matrix A is going to equal our identity matrix I. Now, not all 2 by 2 matrices will have an inverse. In order for it to be invertible, then it must be a non-singular matrix. So in other words, the determinant of A cannot equal 0. So if A is the matrix A, B, C, D, then the inverse matrix of A equals 1 over the determinant of A multiplied by the rearranged matrix called the adjugate or adjoint. Now the adjugate is when we swap the elements A11 and A22 and we change the signs on A12 and A21. So you can see that we are swapping those elements. So we now have D in position A11 and A in position A22. And then we're going to change the signs on our B and C so that we now have -B in position A12 and we have -C in position A21. So the formula for the inverse matrix of A is the adjugate of A divided by the determinant of A. So if the determinant of A equals 0, then A is a singular matrix and it doesn't have an inverse. So the example, find the inverse matrix for A if it exists, where matrix A equals 3, -2, 1, 2. And we then want to show that the pre-multiplication of our inverse is going to give us the identity matrix. So the determinant of A can't be equal to 0 if we're going to have an inverse. So if we substitute 3 times 2, and we're going to take away -2 times 1 into our determinant formula, we're going to get a determinant A of 8. Now this means we've got a non-singular matrix because the determinant of A does not equal 0, and therefore an inverse does exist. So the next thing we want to do is we want to work out what the adjugate of A is going to be. Now remember, for the adjugate of A, we are going to swap A and D, so we're going to end up with 2 and 3 in the opposite positions, and we're changing the sign on our B and C, so we end up with the adjugate of A being 2, 2, -1, 3. And then to work out the inverse matrix, we're taking the adjugate of A and we're dividing that by the determinant of A. So in other words, our determinant of A is becoming a scalar of 1 over 8, and we've got 2, 2, -1, 3 as our adjugate, and now we want to multiply out by that scalar, and we're going to get a quarter, -1/8, and 3/8. And that's our inverse matrix for the matrix A. Now, the last part asked us to show that if we pre-multiply that inverse by the original matrix, we're going to end up with the identity matrix. So we're going to write down that we got our A multiplied by our inverse of A, and that equals 3, -2, 1, 2, multiplied by a quarter, -1/8, and 3/8. And using our multiplication, we're going to do 3 times a quarter and add on -2 times -1/8, which gives us a total of 1. And then we're going to do 3 times a quarter plus -2 times 3/8, which is going to give us a value of 0. 1 times a quarter plus 2 times -1/8 gives us 0 again. And then 1 times 1/4 plus 2 times 3/8 is going to give us a total of 1. And that gives us our identity matrix 1, 0, 0, 1. And so we've proven that we have the correct inverse matrix for matrix A. Now we saw in a previous video that given matrix A equals 2, 3, 1, 4, we could express A squared in terms of matrix A and the identity matrix. From this information, we can express the inverse of A, so our A to the negative 1, in terms of A and I, as we found in our previous video that A squared equaled 6A minus 5I. Now clearly there's no mention of the inverse matrix of A here, so we must introduce it. And we do this by post-multiplying everything by the inverse matrix of A. So we're going to start off with A squared equals 6A minus 5I. And we're going to post-multiply the A squared by our inverse matrix of A, and that's going to equal 6A times the inverse matrix of A minus 5I times the inverse matrix of A. And we're going to split that A squared into A times A, because that's going to help us simplify things. And we're just going to rewrite everything else. But we know that if we pre-multiply the inverse by the original matrix, we're going to end up with the identity matrix. And that is by definition. So that means we have one instance of A post-multiplied by its inverse on the left-hand side and one on the right-hand side. And so we can replace these with our identity matrix. So we end up with A post-multiplied by I equals 6 multiplied by I minus 5I multiplied by the inverse A. Now the other thing that we know is that if we multiply by I, then it doesn't change the original matrix. So we can state here that if we, again, multiplying by the identity matrix does not change the original matrix. And so this time we can rewrite our equation as A equals 6I minus 5 multiplied by the inverse matrix of A. And finally, we can do some rearranging to get the inverse matrix of A isolated. So we've got 5 times the inverse matrix of A equals 6I minus A. And then we're going to divide both sides by 5. And so we get a fifth upon 6I minus A as our inverse expressed in terms of the identity matrix and its original matrix. So, final example, which value of D makes matrix A singular? Well, we know that for a singular matrix, the determinant equals 0. So det A is going to equal 0. Now, we want to work out what the determinant of A is, and we know that it is AD minus BC in terms of the general matrix ABCD. So det A is going to equal negative 3 multiplied by D minus 2 multiplied by 6. And that's going to equal 0 for a singular matrix. So that means we're going to have negative 3D minus 12 equals 0. If we add the 12 to both sides, we're going to get negative 3D equals 12. And if we divide both sides by negative 3, we're going to get D equals negative 4. And that's the value of D that will make matrix A singular.